Good morning and Assalamu alaikum. I am Ali Hajin and Edin from the BS Ed Mathematics, and for today's video I will explain to you the modern algebra and number theory. Modern algebra, also called the abstract algebra, is a branch of mathematics that is concerned with the general algebraic structures of various sets, such as the real numbers, complex numbers, matrices, and vector spaces, rather than the rules and procedures for manipulating their individual elements. During the second half of the 19th century, various important mathematical advances lead to the study of sets in which any two elements can be added or multiplied together to give a third element of the same set. The elements of the sets concerned could be numbers, functions, and some other objects. As the techniques involved were similar, it seems reasonable to consider the sets, rather than their elements, to be objects of primary concern. The definitive treatise Modern Algebra was written in 1930 by the Dutch mathematician Vartel van der Woerden, and the subject has had a deep effect on almost every branch of mathematics. Structures fields. In itself, a set is not very useful, being little more than a well-defined collection of mathematical objects. However, when a set has one or more operations, such as the addition and multiplication defined for the elements, it becomes very useful. If the operations satisfy familiar arithmetic rules such as the associativity, commutativity, and distributivity, the set will have a particularly algebraic structures. Sets with the richest algebra structure are known as fields. Familiar examples of field are the rational numbers, fraction a over b, where a and b are positive or negative whole numbers. The real numbers, or the rational and irrational numbers, and the complex numbers, which are the numbers of the form a positive and negative bi, where a and b are real numbers and I squared is equals to negative 1. From the prehistory through classical Greece, it's the ability to count dates back to prehistoric times. This is evident from archaeological artifacts, such as 1,000 years old bone from a Congo region of Africa, with tally marks scratched upon it, signs of the unknown ancestor counting sometimes. Very near dawn of civilization have the grasp in the idea of multiplicity and thereby had taken the first step toward a study of numbers. Certain that an understanding of numbers existed in ancient Mesopotamia, Egypt, China, and India, for tables, papyri, the temple cravings from these early cultures has survived. The Babylonian tablet known as Plimpton 322 in 7. In addition, in the field mentioned above, which all the infinitely many elements there are, exist fields having only a finite number of elements, always some power of the prime number, and these are of great importance, particularly for discrete mathematics. In fact, finite fields motivated the early development of abstract algebra. The simplest finite field has only two elements. It is the 0 and 1, and 1 plus 1 is equal to 0. This field is application to coding theory and data communication. Next is the structural axioms. The basic rules or the axioms for addition and multiplication are shown in the table, and a set that satisfy all 10 of these rules is called a field. A set that satisfy only axioms 1 minus 7 is called a ring. And if it also satisfy axioms 9, it is called a ring with unity. A ring satisfying the commutative law of multiplication, or the axiom 8, is known as a commutative ring. When axioms 1 minus 9 hold and there are no proper divisors of 0, example, whenever a, b is equal to 0, either a is equal to 0 or b is equal to 0, a set is called an integer domain. For example, the set of the integers negative 1, negative 2, negative 1, 0, 1, and 2 is a commutative ring with unity, but it is not a field because axiom 10 fails. When only axiom 9 fails, a set is known as the division ring or the skew field. Now let's proceed to the number theory. Number theory is a branch of mathematics that is concerned with property of the positive integers 1, 2, 3, and so on, sometimes called the higher arithmetic. It is among the oldest and most natural of mathematical pursuits. Number theory has always fascinated amateurs as well as professional mathematicians. In contrast to their branches of mathematics, many of the problems and theorems of number can be understood by laypersons, although situation to the problem and proofs of the theorems often require a sophisticated mathematical background. Until the mid-20th century, the number theory was considered the purest branch of mathematics, with no direct application to the real world. The event of digital computers and digital communications revealed that number theory could provide unexpected answers to real-world problems. At the same time, improvements in computer technology enabled number theories to make remarkable advances in factoring large number, determining primes, testing conjectures, and solving numerical problems once considered one of the rich. The modern number theory is a broad subject that is classified into subheadings such as the elementary number theory, the algebraic number theory, the analytic number theory, the geometric number theory, and the probabilistic number theory. These categories reflect the method used to address problems concerning the integers. From the prehistory through classical Greece, it's the ability to count dates back to prehistoric times. This is evident from archaeological artifacts, such as 1,000 years old bone from a Congo region of Africa, with tally marks scratched upon it, signs of the unknown ancestor counting sometimes. Very near dawn of civilization have the grasp in the idea of multiplicity and thereby had taken the first step toward a study of numbers. It is certain that an understanding of numbers existed in ancient Mesopotamia, Egypt, China and India for tablets, papyri, and temple carvings from these early cultures has survived. A Babylonian tablet known as a Plimpton 322 in 1700 BC is a case in point. In modern notation, it displays numbered triples x, y, and z with the property that x squared plus y squared is equal to z squared. One such triple is 2,291, 2,700, and 3,541, where 2,291 squared plus 2,700 squared is equals to 3,541 squared. This certainly reveals a degree of numbers theoretic sophistication in ancient Babylon. Despite such isolated results, a general theory of numbers was non-existent. For this, as with so much of theoretical mathematics, one must look to the classical Greek, whose groundbreaking achievement display an odd fusion of the mystical tendencies of the Pythagoreans and served logic of Euclid's elements in 300 BC. According to tradition, Pythagoras in 580 to 500 BC worked in southern Italy amid devoted followers. His philosophy enshrined number as the unifying concept necessary for understanding everything from planetary motion to musical harmony. Given this viewpoint, it is not surprising that the Pythagoreans attributed quasi-rational properties to certain numbers. For instance, they attach significance to perfect numbers. Example, those that equal the sum of their property divisors. For examples are 6, whose property divisor is 1, 2, and 3. Sum to 6. And the 28, which is the 1 plus 2 plus 4 plus 7 plus 14. The Greek philosopher Nicomachus of Gerasa flourished CAD 100, writing centuries after Pythagoras, but clearly to his philosophical depth, stated that perfect numbers are represented. Virtues, wealth, moderations, property, and beauty. Some modern writers label such nonsense numerical theology. In a similar vein, the Greek called a pair of integers amicable, or the friendly. If each was the sum of the proper divisor of the other, they knew only a single amicable pair, 220 and 284. One can easily check the sum of the property divisor of 284 is 1 plus 2 plus 4 plus 71 plus 142 is equals to 220. And the sum of the proper divisor of 220 is 1 plus 2 plus 4 plus 5 plus 10 plus 11 plus 20 plus 22 plus 44 plus 55 plus 110 is equals to 284. For those prone to number mysticism, such as the phenomenon must have seemed like magic. By the contrast, Euclid presents the number theory without the flourishes. He began Book 7 or his Elements by defining a number as a multitude composed of units. The plural here exclude 1. For the Euclid, 2 was the smallest number. He later defined a prime of a number measured by unit alone. Example, whose only proper divisor is 1. A composite of a number that is not prime and a perfect number is one that equals the sum of its parts. Example is its proper divisors. From there, the Euclid proved a sequence of theorems that marks the beginning of the number theory as a mathematical as composed to the numerological enterprise. For Euclidean professions deserve special mention. The first profession 2 of Book 7 is the procedure of finding the greatest common divisor of the whole numbers. The fundamental result is now called the Euclidean algorithm in his honor. Second, Euclid gave a version of what is known as the unique factorization theorem or the fundamental theorem of arithmetic. This says that any whole number can be factored into product of primes is in one and only one way. For examples is 1960, where it is equals to 2 times 2 times 2 times 5 times 7 times 7 is a decomposition into prime factors, and no other such decomposition exists. Euclid's discussions of unique factorization is not satisfactory by the modern standard, but its excess can be found in Proposition 32 of Book 7 and Proposition 14 of Book 9. Third, Euclid showed that no finite collection of primes contains them all. His argument, Proposition 20 of Book 9, remained one of the most elegant proofs in all of the mathematics. Begin with any finite collection of primes, says A, B, C, or N. Euclid considered the number form by adding one of their product, where N is equals to A, B, C, and N plus 1, and then examine the two alternatives. Take note that if N is a prime, then it is a new prime not among A, B, C, because it is larger than all of these. For example, if the original primes were 2, 3, and 7, then N must be equals to quantity 2 times 3 times 7 plus 1. It is equals to 43. 43 is the larger prime. Of later Greek mathematician, especially the noteworthy is Diophantus of Alexandria, the author of Arithmetica. This book features a host of problems, the most significant of which have to come and be called the Diophantine equations. These are equations whose solution must be whole numbers. For example, Diophantus asks for two numbers. One is square and the other one is cube. Such the sum of their squares is itself a square. In modern symbol, the sought integer x, y, and z, such the x squared quantity squared plus y squared quantity squared is equals to z squared. It is easy to find real numbers satisfying this relationship. Example: x is equals to square root of 2 and y is equals to 1 and z is equals to square root of 5. But the requirements that solution be integers make the problem more difficult. One answer is x is equals to 6, y is equals to 3, and z is equals to 45. Diopantus' work strongly influenced the later mathematics. Now let us proceed to the number theory in the East. The millennium following the decline of Rome saw no significant European advances, but Chinese and Indian scholars were making their own contribution to the theory of numbers. Motivated by questions of astronomy and the calendar, the Chinese mathematician Sun Tzu tackled multiple Diophantine equations. As one example, he asked for a whole number and when divided by 3 leaves off remainder of 2. When divided by 5 leaves a remainder of 3. When divided by 7 leaves a remainder of 2. His answer is 23. Almost 1,000 years later, Owen Jiusao gave a general procedure now known as the Chinese remainder theorem for solving problems of this sort. Meanwhile, the Indian mathematicians were hard to work. In the 7th century, Brahmagupta took up what is now the erroneously called the Pell equation. He posed the challenge to find a perfect square that, when multiplied by 92 and increased by 1, yields another perfect square. That is, he sought whole number x and y such as 92 92x squared plus 1 is equals to y squared minus a. Diophantine equation with quadratic terms. Brahmagupta suggested that anyone who could solve this problem within a year earned the right to be called a mathematician. His solution was x is equals to 120 and y is equals to 1151. In addition, Indian scholars developed the so-called Hindu-Arabic numbers. The base 10 notation subsequently adopted by the world's mathematical and civil communities. The C numerals and numbers numeral system. Although more number representation than number theory, these numerals have prevailed due to their simplicity, the ease of use. The Indians employed this system, including the zero, as early as AD 800. At about this time, Islamic world became a mathematical powerhouse situated on trade routes between East and West. Islamic scholars absorbed the works of other civilizations and augmented these with homegrown achievements. For example, the Thabit ibn Qura, or the active in Baghdad in the 9th century, returned to the Greek problem of amicable numbers and discovered a second pair, 17,296 and 18,416. Now let us proceed with the modern number theory. As a mathematics filtered from the Islamic world of Renaissance Europe, number theory received little serious attention. The period 1000 from 1400 to 1650 saw important advances in geometry, algebra, and probability. Not to mention the discovery of both logarithms and analytical geometry, but number theory was regarded as a minor subject, largely of recreational interest. Let us now proceed to the Pierre de Fermat. Credit for the changing this perception goes to Pierre de Fermat in 1601 to 1665. A French magistrate with time in his hand and a passion of numbers. Although he published a little Fermat posed the equations and identified the issues that have shaped numbers theory ever since. Here are the few examples. In 1640, he stated that is known as Fermat's little theorem, namely, that if P is prime and A is any whole number, then P divided evenly into A raised to P. Thus, if P is equals to 7 and A is equals to 12, the far from obvious conclusion is that 7 is a divisor of 12 raised to 7 equals to 12 is equals to 35,831,796. This theorem is one of the great tools of modern number theory. Next is the Fermat investigated the whole types of odd primes, those that are 1 more than a multiply of 4 and those that are 1 less. These are designed as the 4k plus 1 primes and other 4k minus 1 primes. Respectively, among the former are 5 is equals to 4 times 1 plus 1 and 97 is equals to 4 times 24 plus 1. Among the latter are 3 is equals to 4 times 1 minus 1 and 79 is equals to 4 times 20 minus 1. Fermat asserted that any prime of the form 4k plus 1 can be written as the sum of 2 squared in one and only one way, where a prime of the form 4k minus 1 cannot be written as the sum of 2 squares in any manner whether thus 5 is equals to 2 raised to 2 plus 1 squared and 97 is equals to 9 squared plus 4 squared, and these have no alternative decomposition into sum of squares. On the other hand, 3 and 79 cannot be decomposed. This dichotomy among prime rank as one of the landmarks of the number theory. The second assertion is one of the most famous statements from the history of mathematics. While reading Diopantus' Arithmetica, Fermat wrote in the book's margin to divide a cube into 2 cubes, a fourth power, or in general any power whatever into 2 powers of the same denomination about the second is impossible. He added that -1 assuredly found in admirable proof of this, but the margin is too narrow to contain it. In symbol, he was claiming that if n is greater than 2, there are no whole numbers x, y, z such that x raised to n plus y raised to n is equals to z raised to n. A statement that came to be known as the Fermat's last theorem. For 3.5 centuries, it defeated all who attacked it, earning a reputation as the most famous unsolved problem in mathematics. But despite Fermat's genius, number theory still was relatively neglected. His reluctance to supply proof was partly to blame. But perhaps more detrimental was the appearance of the calculus in the last decade of the 17th century. Calculus is one of the most useful mathematical tools for all, and scholars early applied its idea to the range of real-world problems. For contrast, number theory seemed too pure, too divorced from the concern of physicists, astronomers, and engineers. Now let us proceed to number theory in the 18th century. Credits for bringing the number theory into the mainstream. For finally, realizing Fermat's dream is due to the 18th century's dominant mathematical figure, the Swiss Leonhard Euler. Euler was the most prolific mathematician ever and one of the most influential, and when he turned his attention to number theory, the subject could no longer be ignored. Initially, Euler shared the widespread indifference to his colleagues, but he was in correspondence in Christian Goldbach, a number theory enthusiast acquainted with Fermat's work like an assistant salesman. Goldbach tried to interest Euler in the theory of numbers, and eventually his existence paid off. It was later on December 1, 1729, in which Goldbach asked Euler, "Is Fermat's observation known to you, and that all numbers 2 raised to 2n plus 1 are primes?" This quotes Euler's attention indeed. Indeed, he showed that Fermat's assertion was wrong by splitting the number 2 raised to 25 plus 1 into the product of 641 and 6,700,417. But through the 5 next decades, Euler published over 1,000 pages of the research on number theory, much of it furnishing proofs of Fermat's assertions. In 1736, he proved Fermat's lethal theorem that is cited above. By mid-century, he had established Fermat's theorem that primes of the form 4k plus 1 can be uniquely expressed as a sum of 2 squared. He later took up the matter of perfect numbers, demonstrating that any even perfect number must be assumed from the form discovered by Euclid 20 centuries earlier. And when he turned his attention to amicable numbers in which by his time only three pairs were known, Euclid vastly increased the word supply by finding 58 new ones. Of course, even Euler could not solve every problem. He gave proofs or near proofs of Fermat's last theorem of exponents n is equals to 3 and n is equals to 4, but despaired of finding a general solution, and he has completely stumped up by Goldbach's assertion that any even numbers greater than 2 can be written as the sum of two primes. Euler endorsed the result today, known as the Goldbach conjectures, but acknowledged his inability to prove it. Euclid gave another number theory a mathematical legitimacy. The thereafter progress were rapid. In 1770, for instance, Joseph Louis Lagrange proved Fermat's assertion that every whole number can be written as the sum of the four and fewer squares. Soon thereafter, he established a beautiful result as the Wilson's theorem. P is a prime if and only P divided eventually into P quantity P minus 1 times P minus 2 quantity. For immense significance was the 1801 publication of Disquisitions Arithmeticae by Carl Friedrich Gauss in 1770 to 1855. This became, in a sense, the holy right of numbers theory. In the Gauss organized and summarized much of the work of his predecessors before moving boldly to the frontier of research, observing that the problem of resolving composite numbers into prime factor is one of the most important and useful in arithmetic. Gauss provided the first modern proof of the unique factorization theorem. He also gave the first proof and the law of quadratic reciprocity, a deep result frivolously among the numbers. To excite his work, Gauss introduced the idea of congruence among numbers. He defined A and B to be congruent modulo. M written A is equals to B and mode is equals to M. If M divides evenly into the difference A minus B, for instance, 39 is equals to 4 mode 7. This innovation, when combined with results like Fermat's little theorem, has become an indispensable features of number theory. For the classical to analytical number theory, inspired by the Gauss, other 19th century mathematicians took up the challenge. Sophie Germain in 1776 to 1831, who once stated, -1 have never ceased thinking about the theory of numbers, made important contribution to Fermat's last theorem, and Adrien Marie Legendre in 1752 to To 1833, the Peter Gustav Lejeune Dirichlet in 1805 to 59 confirmed the theorem for n is equals to 5 minus I e. They showed that the sum of the fifth power cannot be a fifth power. In 18 in 1847, Ernst Kammer went further, demonstrating that the Fermat-Last theorem was true for a large class of exponents. So that unfortunately he could not rule out the responsibility that it was false of the large class of exponents, and so the problem remained unresolved. The prime number theorem was one of the supreme achievements of 19th century mathematics. That was the prime number theorem. And it is worth a brief digression. To begin, designated the number of prime less than or equal to n by pi quantity n, thus pi quantity 10 is equals to 4 because 2, 3, 5, and 7 are the 4 prime not exceeding 10. Similarly, pi quantity 25 is equals to 9 and pi quantity 10 is equals to 25. Next, consider the proportion of number less than or equal to n that are primes. Clearly, pi quantity 10 over 10 is equal to 0.40, meaning that 40% of the numbers not exceeding 10 are prime. The pattern is anything but clear, but the prime number theorem identifies one, at least approximately, and verbally provide the rule of distribution of primes among the whole numbers. The theorem says that for large n, the proportion pi n all over n is roughly 1 over log n, where log n is the natural logarithm of n. This link between primes and logs is nothing short of extraordinary. And now let us proceed to the number theory in 20th century. The next century saw an explosion in number theoretic research along with the classical and analytical number theory. Scholars explore specialized subfields such as algebraic number theory, geometric number theory, and combinatorial number theory. The concept become more abstract and the techniques become sophisticated. Unquestionably, the subject had grown beyond Fermat's wildest dream. One of the great contributions from early in 20th century was the incandescent genius Srinivasa Ramanujan in 1887 to 1920. Ramanujan, whose formal training was limited as his life was short, brushed upon the mathematical scene with a series of brilliant discoveries. Analytical number theory was among his specialties, and his publications carried titles such as Highly Composite Number and Proof that Almost All Numbers n are composed of about log or the log n prime factors. A legendary figure in 20th century number theory was Paul Erdos in 1913 to 96, a Hungarian genius known for his deep insight, his vast circle of collaborators, and his personal eccentricities. At the age of 18, Erdos published a much simplified proof of a theorem of Chevy stating that if n is greater than 2, then there must be a prime between n and 2n. This was the first in the string of the number theoretic result that would span most of the century. In the progress, Erdős, who also worked in combinatorics, graph theory, and dimension theory, published over 1,500 papers with more than 500 collaborators from around the world. He achieved his astonishing output while living more or less out of suitcase, traveling constantly from one university to another in pursuit of new mathematics. It was not uncommon for him to arrive unannounced with the declaration that my brain is open, and then he plugged into the latest problem with gusto.